right? When we were out of school or whatever, I left the video for you guys. Does that sound right? Yes. Okay. Good. All right, so today we're going to do the rest of chapter 6. So we have 2 more types of identities to talk about, the power-reducing identities, the half-angle identities, and then a little bit of solving talk to have at the very end, but it's not so bad. So there's 3 power-reducing identities that we give. Now, typically we only list these 3 if you wanted the power-reducing identity for like cosecant, secant, or cotangent. What do you suppose we're going to do? Just do the reciprocal of the one for the corresponding sine, cosine, or tangent, right? No big deal. Okay. So let's just look at a quick example here, or 2. So let's evaluate some stuff using the power-reducing identity. So let's say we have cosine squared of 60 degrees. So we'll just use the power-reducing identity where u is 60. So go ahead and plug this all in. So far, so good. 2 times 60 is 120. If I go to my unit circle, cosine of 120 is 1/2. I'm sorry, negative 1/2. One plus negative 1/2 is just 1/2. And 1/2 divided by 2 is 1/4. We okay with that? Okay. Let's say we want to do cotangent squared of negative 165. Notice that we don't have a power-reducing identity written down for cotangent, but that's okay. I mean, we're just going to do the reciprocal of the tangent one. Since I know tangent and cotangent are reciprocals, cotangent squared u should just be the reciprocal of tangent squared u. No big deal. Everybody okay with that notion? Okay, so we go ahead and plug our things in. 2 times negative 165 is negative 330. And negative 330 degrees is not a unit circle angle, is it? What do we do? Well, maybe something coterminal to it is a unit circle angle, right? My unit circle angles are all positive. So what do I need to do to find something coterminal to this that is going to be positive, Ella? Yeah, we're just going to add 360. So negative 330 plus 360 is just 30 degrees. And now I can go to my unit circle and pull the value for cosine of 30 degrees, which is root 3 over 2. Now, this is not the final answer we'd want to leave because, well, we got fractions inside of fractions. We'd prefer to simplify it better than that. So the easiest way to simplify this down is we'll just multiply the top and bottom of this fraction by 2. So that's going to distribute through when we multiply two fractions together. So 2 times 1 is just 2. 2 times root 3 over 2, the 2's cancel and you're left with just the root 3. And then same thing in the denominator. Okay to hear? Now, is this answer a good place to leave it at? We can do better than this. What's wrong with this? Got a radical in the denominator, right? We typically don't want to leave an answer with a radical in the denominator. So what are we going to do to get the radical out of the denominator here? Think back to your Algebra 2 class last year. You'll remember that when we have addition and subtraction of a radical in the denominator, the trick here is to multiply by the conjugate. So the conjugate is like the same thing as the denominator with the opposite sign in the middle. So we're going to multiply the top and bottom by 2 plus root 3. And then we'll really kind of think about these all have parentheses around it, because what we're going to do here is to FOIL. So I'll write out the foiling. Just FYI, square root of 3 times square root of 3 is square root of 3. Square root of root 3 squared, or just 3. I'm just going to write it as 3 and do that simplifying kind of in my head. Now, if we combine like terms here, you notice in the denominator I have a positive 2 root 3 and a negative 2 root 3. So those are going to just combine to give us 0. And then I have 4 minus 3, so that's just going to be a 1 down there. And then the numerator, 4 and 3 is 7. 2 root 3 plus 2 root 3 is 4 root 3s. And really, we don't need that 1 there. We can just write our final answer as 7 plus 4 root 3. So that's kind of as bad as it's going to get. Notice the trigonometry part wasn't very hard. It was a lot of hassle, like simplifying the final answer to get something respectable. Doing the algebra piece from last year was kind of the hassle of this, but like basically just plug stuff into a formula, you know, and then grind. Let's look at a proof example that we can use these power reducing identities on. So let's say we have sine cubed equals 1/2 sine x times the quantity 1 minus cosine 2x. Now, one of the things we talked about when we did these proofs in chapter 5 was usually we like to start on the more complicated side and work towards the simpler side. That notion kind of goes away now that we have access to these newer identities that take something simple and make something complicated, right? If you look at the angle sum and differences or the double angles or now these power reducings, each one of them takes something kind of simple and creates something kind of complicated. So on a problem like this, I'm probably going to try to start on the simple side, the left-hand side, and try to end up at the right-hand side. Will probably be a little bit easier. So one thing I notice is that on the left-hand side, I have just x's, and on the right-hand side, I have x's and 2x's. One of the best ways to go from regular x's to getting 2x's is using the power-reducing identity. But I need a sine squared in order to do that. So the first step, what I'm going to do is I'm just going to think about sine cubed as sine times sine squared. And the reason I like doing that is because then I can employ the power reducing identity for sine. And I notice that I have here 1 minus cosine 2x all divided by 2. I know that dividing by 2 is the same as multiplying by a half. And I can multiply in any order I want, so I can like pull that 1/2 all the way out to the front. And that's what I need. Woo! That ain't too bad. Let's do another. So here we have cosine to the 4th x plus equals 3 plus 4 cosine 2x plus cosine 4x all over 8. So right away I notice that on the left-hand side I have just x's, on the right-hand side I have 2x's and 4x's, and so I'm pretty sure I'm going to be using the power reducing identity at least twice, right? That's how I'm going to go from 2x to 4x or whatever. So my first step would be, again, to just rewrite cosine to the 4th so that I have squareds in there so I can use my power reducing identities. So cosine squared is 1 plus cosine 2x over 2. So I have that twice. Everybody cool with that? If I multiply the numerators out, I'd have to FOIL that. I'm just going to write out the FOILed out solution here rather than show all the silly little steps. And then we multiply the denominators together. Everybody okay to hear? So now what I'm going to see is, okay, I have another cosine squared, so I'm going to do the power reducing on that one. I knew that I was going to have to do the power reducing at least twice. So this is the step that I was anticipating. Notice there that when I did the power reducing on cosine squared 2x, I get 1 plus cosine of 2 times 2x. Everybody's okay with that? And obviously 2 times 2x is 4x. There's the 4x that I was expecting to get at some point. The last thing I would probably worry about here is I need to get just like a single fraction rather than fractions inside of fractions. So I'm going to do that same trick that I did before and multiply the top and bottom by 2. So that 2 is going to distribute. So 2 times 1 is 2. 2 times 2 cosine 2x is 4 cosine 2x. And then 2 times 1 plus cosine 4x over 2, just the 2's are going to cancel, so I'll be left with 1 plus cosine 4x. And then 2 times 4 is 8. Hi, Joe. And then the last thing I really need to do is just add the 1 and the 2, and I got what I'm looking for, right? Yeah, why not? Okay. The next up are these half-angle identities. Again, with the half-angle identities, we really only write the sine, cosine, and tangent versions, because if you needed the reciprocal version, you can just like make the reciprocal. Although those versions, like to write the closed form of it is kind of a pain in the tuchus, because you have the square root, so you potentially want to be rationalizing denominators, and it gets ugly to write that. Now, for what you'll be doing with these, it's not necessary to like rationalize the denominator. If you're just going to be evaluating the thing, you can just like, don't have to rationalize the denominator in the formula. You can just wait till the end and just rationalize whatever your answer is. You know what I mean? But if we're going to write the formula down, we should rationalize the denominator then, which just gets kind of yucky looking. Worth noting that we that we have 3 different versions of the half-angle identity for tangent. So depending on what you're doing, some of these may seem easier to use than the other. So when using this one, we'll want to be a little bit careful about which one we pick. Okay. So let's say, again, we want to evaluate using our half-angle formulas. So let's say we have sine of 9 pi over 8. My first step here is to rewrite 9 pi over 8 as something divided by 2. Well, that's not difficult to do, all I really need to do is multiply 9 pi over 8 by 2, and then just write it over 2. Now I reduce 9 pi over 8 times 2 to be 9 pi over 4. Everybody's okay with that? Okay. So when I plug this in, I have plus or minus square root of 1 minus cosine of 9 pi over 4 divided by 2. Now, right here, let's deal with this plus or minus and figure out which one is which. The way we figure that out is we look at the original angle measure, right? The problem we're trying to do is sine of 9 pi over 8. What quadrant is 9 pi over 8? Or is the standard position angle, or terminal side of the standard position angle 9 pi over 8? What quadrant is that in? Oh, guys. 0, pi over 2, pi. So it's got to be over here past pi, right? Because 9 pi over 8 is bigger than pi. Everybody agree? So that's in Q3. And in Q3, is sine positive or negative? Negative, right? Again, we did just all silly turtles crawl to kind of figure that out. So which one should we use? The negative version. Everybody okay with that? So not difficult to do, but you have to remember to do it. Okay, come back. And you have to remember that you're using the original angle, not 9 pi over 4, but we're using the original problem, 9 pi over 8. Okay? All right. Next up, we'll go to the unit circle and try to look up cosine of 9 pi over 4, but oopsie-daisy, 9 pi over 4 is in a unit circle angle. Oh no, whatever do I do? I'll find something coterminal to it by doing subtracting 2 pi. When I subtract 2 pi from 9 pi over 4, I get pi over 4. I made a common denominator while I did that, and I just did it in my head. I hope you're all okay with that. Now I can go to my unit circle, look up cosine of pi over 4, which is just root 2 over 2. I can do better than this answer, though. Why? It's fractions inside of fractions, right? What's going to be the trick to get rid of that fraction inside of fractions? I'll multiply the top and bottom by. Anybody? You'd say 2 over 2. That's not quite right, though. You want square root of 2 over 2. Why do I need the square root there? Not so it can take out the square root in the first place, but so you can multiply under the square roots, right? If I do square root 2 times square root 3, that's square root 6. I can multiply the stuff underneath the radicals together. If I did square root 2 times 3, that's just 3 square root 2s, right? You can't multiply something under a square root with something outside of a square root. Okay? But the same kind of thing, we just multiply the 2's now. Everybody's okay with that? But we can do a little bit better than this. What can we still do? Remember that the square root of a fraction is the square root of the numerator over the square root of the denominator. And the square root of 4, well, heck, that's just 2, right? Everybody's okay there? I'm going to warn you guys about this when you're writing your own work. Be really mindful about when you're drawing the radical, making sure if you're talking about the radical of the entire fraction, that it's really clear that that radical is over the entire fraction versus a radical that's over just the numerator, making sure that you draw your radical over just the numerator. As the teacher, I can only grade what you've written down on my paper, and if it's not really clear what you're doing, I can't assume that you're doing the right thing, right? You have to make sure you're being pretty clear about that, in particular on problems like this where part of the problem, the radical's over the entire fraction, part of the problem, the radical's only in the numerator. Got to be careful. Okay? But just wanted to point that out to you because it's a place where we can get a little careless, and without the, with no narrative, I have to just mark what I see. You know what I mean? Okay. Let's do one more of these, and then we'll do a proof or something. So we'll do cotangent of -105. Well, the first thing I want to do is rewrite that as a half angle. But that's not too bad. I can just do -210 over 2. Right? I just multiply 105 by 2 and then write it over 2. Same thing. Just like we did in the previous problem where I just multiplied 9 pi over 8 by 2 and wrote it divided by 2. Right? Multiplying by 2 and then dividing by 2, nothing changed. Everybody cool with that? Okay. Now let's go retrieve our half angle identity. So because we're looking at cotangent, we're going to be looking at the reciprocals of these tangent identities. So which one would I want to use? There is a best answer here. All answers are appropriate, depending on how much appetite you have for potentially some crummy simplification. But there's a best answer in terms of the easiest route to a simplified answer. So which one is probably out right away? I mean, I would hope you would say the first one, right? It has the square root on it, it has the plus or minus. I'd prefer not to have to mess with either one of those two things if I don't have to. I agree. So it leaves just the second and third version here. So the difference between the two versions is one of them has a single thing in the denominator, one of them has addition and subtraction in the denominator. Which one is going to be easier for us to simplify or poses less risk when it comes to simplifying? Where you'd have a single thing in the denominator, right? The reason being, if we have to rationalize the denominator, it's much easier if that denominator is just like square root of 2 versus 1 plus square root of 2. Like the algebra just gets simpler. But because we're doing cotangent, we're looking at the reciprocals of these things. So I'm actually going to use the third one because when I flip it, that leaves just a single thing in the denominator. I want to be clear, though, there isn't like a wrong answer to that. It's just a best answer kind of thing. Okay. And again, -210. Oh no! Whatever shall I do? Just add 360 to it. It's no big deal. We've done this a bunch of times now. If I go to my unit circle, cosine of 150 is negative root 3 over 2. Sine is positive 1/2. Multiply the top and bottom by 2. And I'm left with 2 plus root 3 over 1. I'm not going to bother with the 1. What'd you think on that? Not so bad.
So why did I go from 1 plus codes to...
Oh, why did it do that? I don't know, because I wrote down the wrong thing, huh? Thanks. Good catch. I appreciate you saying something. If it ever looks like I made a mistake, feel free to ask. I will not be upset about that, even if there was no mistake, because it probably dealt with needing to explain something. Yes, Maddie. Of course. Okay. Let's do a proof. So here, what catches my eye is the x over 2. I notice that half angle right away. On the right-hand side, there are no half angles. So I think I would start on the left-hand side and start by trying to get rid of the half angle using one of my half angle identities. Now observe here that the half angle identities are for like cosine of x over 2. Here we have cosine squared x over 2. So what I'm going to do is I'm just going to use the half angle identity twice. Right? Because cosine squared x over 2 is just like cosine x over 2 times cosine x over 2. So I did the cosine x over 2 squared, right? Is that okay? You guys see what I did there? I guess I'll finish writing the rest of that stuff. But I love seeing that, right? Love, love, love that. Because what's the squared going to do? Gets rid of the plus or minus because anything squared is positive, so I don't have to worry about that. And it's going to cancel the square root, which is like just pretty righteous deal. And then, whoa, even better, look at this. I have a times 2 and a divides by 2. I guess I should probably just make sure that I go all the way. Whoa, out of here. This is starting to look pretty nice. I guess now distribute the secant. And I know cosine times secant, well, those two things are reciprocals, right? Cosine and secant. So when I multiply them together, they just have to give me 1. I'm going to skip the steps in showing that because I think you guys are probably cool with filling in those steps on your own if you need to. And in the interest of time, I'm just going to skip those extra line or 2 of writing. You should write those out on a test or whatever. I'm just going to talk about it since we're doing notes or whatnot. Is that okay? Cool. Last section is 6.4, which is all just proofs and solving. So previously to this point, we had seen that the proofs that we had done had kind of followed with whatever the identity we were studying in that section, so it was kind of obvious what to choose. Here, we're going to look at a couple of proof, well, I guess just one, I think, is all I really wanted to talk about. But we're not going to give you like any indication of which identities you might want to use. Okay, so if I go, oh boy, you really did that, huh? So the thing that catches my eye is the 2 alpha. Everybody's good with that? Particularly since the other side just has regular alphas. So I'm going to want to use some kind of identity that can get rid of that 2 alpha and replace it with just regular alphas. So I could use, like a sum identity where I can write 2 alpha as alpha plus alpha. Or I can just use the double angle. That seems like the better choice to me because it looks a little nicer than that thing was. You know what I mean? So let's do that. But remember, we're doing cotangent is the function that we have in our example. So we're going to be using the reciprocal of this one. So I'm going to write 1 minus tan squared over 2 tan. So I still have that 2 out front. And all right, times 2 divides by 2. Get that stuff out of here. I like that because if I look at the right-hand side, there's definitely no coefficients over there, so I'm glad to get rid of that. Now, if I look at the right-hand side, I have 2 separate things, right? I have cotangent minus tangent. So what I think I would want to do is I'm going to rewrite this single fraction as 2 fractions with the same denominator. So I can write 1 minus tangent squared x all over tangent x as 1 over tangent x minus tangent squared over tangent x. Everybody's okay with me kind of splitting up that compound fraction into 2 separate fractions like that? And the reason I thought to do that again was I saw that I had 2 separate things over here. So it's like, okay, I have 1 fraction, I got to break that up into 2 things. Let's just do it now. And I like that because, well, the tangent and the tan squared can just reduce and become tangent. And 1 over tangent, well, the reciprocal identity just says that's cotangent. And what the heck, I'm done. Whoa! That wasn't so bad. Now, if you had attempted to use different identities or gone about doing different algebra or whatever, like, it could have been a mess. But just because we have these new identities and it's like, boy, that 2 stuff doesn't look at all the same kind of thing. Usually the same kind of, like 3 to 5 steps is kind of the norm. If you're doing it the best way. If you don't choose the best way, like it can balloon and you can end up with like 10 steps or something, and it's okay. That's not a big deal. We're not giving out style points here. I wish I would. I'm just joking. So let's do a couple more solving examples here to show you how these new identities can really help make our solving a little bit easier. So let's say we have cosine 2x equals sine x, and we're solving that on the interval from 0 to 2 pi. So if you remember last chapter, whenever we ran into one of these situations where we had a coefficient on our x, this kind of made life a little bit of a hassle, right? We had to start by finding the infinite solution. And then when we divided that 2, it changed what was the coterminal amount. And then we had to make sure we generated all of our solutions inside the interval and all that nonsense. You remember kind of doing that? The alternative now is I can use an identity to just rewrite everything so that it has x's. I don't have to worry about that ever again, which is what I prefer to do. So I'm going to go ahead and go to my identity list and look for something that I can replace this cosine 2x with, so that I have just x's. So I go and I do that. I can do an angle sum, right? I can do x plus x, but I got all this stuff. Or if I use the double angle, that's probably what I prefer. I have 3 choices. So of these 3 choices, which one is going to be the best one for me in order to solve this thing? There is a best answer here. Mia? The last one, exactly. Why? Right, because it has only sine x's in it. The other trig identity in my problem has sine x's in it. So that's why I want to use the one that also has sine x's in it. So I have just one type of trig function now. That makes life typically much easier. All right. So this looks a little quadratic-y with me because I have a sine squared, I have a sine to the first, and I have a constant. So I'm going to get everything onto one side. So I'm going to add the 2 sine squared over and then subtract the 1 over. To factor something that has a leading coefficient, I want to find the 2 things that multiply to give me the leading coefficient times the constant term, but add to give me the null term. So multiplies to give me -2, adds to give me 1. I mean, 2 and -1. It's the same 2 things I multiplied together. So I use the 2 and the -1 to rewrite the middle term as sine 2x plus -1 sine x. So I can make 2 groups. From the first group, I can take out a greatest common factor of 2 sine x. From the second group, I can take out a greatest common factor of a -1. Since each of these have a sine x plus 1 in common, I can factor that out, which leaves me with the 2 sine x minus 1. So there's my factored form. Now that I've factored this, I can set each of these factors equal to 0 and solve them. So I subtract 1 from both sides. So there I'm going to do the sine inverse of -1. When I go to my unit circle, that is 3 pi over 2 is the only place that -1 occurs as a y-coordinate. For the other equation, I'm going to add 1 and divide by 2, so I have the sine inverse of 1/2. I go to my unit circle and look for where the y-coordinate is 1/2. That happens at pi over 6 and 5 pi over 6. So those are my 3 solutions. Notice here at no point did I have to divide by 2 when solving for x, right? Once I got the x by itself. I didn't ever have to do anything with that. That's the point of doing it this way, is that we can avoid having to do the coterminal stuff. And just whatever we pull from the unit circle is what we pull, which is the way I prefer to do it, right? It's kind of a hassle doing it that other way. Let's do one more and call her a day. How's that sound to you guys? Okay, I'm good with that too. Okay, so I take a look here. Thing that jumps out to me is the theta over 2. I don't like the divide by 2 because I know when I have to go to solve that thing, it's going to make my life a pain. So the first thing I'm going to do is use a half angle to get rid of that. You could also do a power reducing. You'll end up at the exact same spot. I usually think of the half angles first because when I see the half angle, that's what I'm thinking. Notice though that it was thankfully sine squared attached to the half angle, so we get that same canceling that we had observed before. Like, woo, that is some nice stuff. Where I lose the radical and the plus or minus and the squared. And then as we observed before, I have a times 2 and a divides by 2. Get rid of those. Now what do I do here? I have a sine squared and I have a plus 1 and I have a minus cosine. It seems like I'm stuck, right? No, man, we're good. Sine squared I can write as a cosine, right? In terms of cosines. Sine squared is just 1 minus cosine squared. Righteous. So I subtract 1 from both sides and then add cosine squared to both sides. And I have this, which is beautiful because it's super easy to factor that. Just take off the greatest common factor of cosine. Then I can set each piece equal to 0 and solve. So theta's cosine inverse of 0. The x-coordinate is 0 at pi over 2 and 3 pi over 2. And then here we'll add 1 to both sides and then do the inverse. The cosine inverse of 1 is just at 0. So when I write my final answer, I can say theta is pi over 2 plus pi k, where k is an integer. And I can say 0 plus, 2 pi k, where k is an integer. Notice that with pi over 2 and 3 pi over 2, those guys are just pi apart. So I combine those two solutions into the one statement here by making that pi k. If you wrote them as two separate ones with 2 pi k's, that's still correct. Would not be deducted for doing that. Everybody's okay? That's going to wrap us up for chapter 6. Reminder again that all of the chapter 6 materials that I would given you guys to work on in chapter 6 are there in the content library. You can do as much or as little of that as you like, but chapter 6 is represented on the exam. The exam questions are going to come exactly from the chapter 6 test, so I think at minimum you should at least do the Chapter 6 test and feel good about that. So the test is there in the content library. So the first two pages are just finding exact values using the different types of identities like we've done before. And there's 2 proofs and 2 solvings. The key is up also in the content library, so you can kind of check your work with my complete worked out solutions, as well as like the review and the key for that, a worksheet and the key for that, the odd solutions to the problem set, all the normal jazz, all in there for you guys. Everybody sound okay? Reminder again for the final exam, you're allowed to have 1 sheet of paper notes. Those notes need to be handwritten. They can be on one side of the sheet of paper. And in order to use them, you have to turn them in to me by the end of the day on Wednesday, December 15th. So 2:45, December 15th, I need to have that 1-page sheet of notes. I'm going to hold on to that until the final exam and then give it back to you at the exam time. If you bring your own notes to the exam day, I will not let you use them. They have to be turned into me in advance by Wednesday, December 15th at 2:45 is the last day and time I will accept them. Any time before that is okay, though. So if you spend the weekend making up your note sheet and you want to turn that in on Monday, I am definitely super cool with that. If you want to wait till the very last minute, that is okay. If you turn it in and 2 days late and a day later you're like, hey, can I have that back? I want to add something else to it. Super okay. Super okay. Up until the end of the day on Wednesday, December 15th, you can take things back and add things to it. No problem. Okay? So the next class day is the retake. If you wanted to do the retake, you would have need to sign up for that on the Google form and get that submitted by the end of the day today. If you've already done that, I've already started printing the retake versions for you guys, so I'm ready on that. I think I have, 40 or so people still left to submit their form, but I got 100 in. I got like about 140 students, I think I counted. If you're not doing a retake next class, that time is yours to work on whatever is your highest priority item, whether writing your review sheet or working on the old tests or whatever. That time is yours to do with what you'd like, although we do need to have like a test-friendly environment for those people that will be doing retakes. And then the last class before the final, again, is your time. You can ask individual questions. That's fine at any of these points along these next 2 days. I don't plan on doing like a stand at the board review at any point. I'm just going to let you guys work because you have the tests and the answer keys for everything. So I think that by Friday I'll have the 4 and 5 chapter keys in there. I just waiting on a couple of people that are still finishing their makeup tests for those things. Oh my God, really? Yes. But that'll all be up